Hello, fellow problem solvers. So today we're going to be doing this pretty cool, it seems simple, but it's not, problem from the Chilean National Math Olympiad from 2015, problem number 4. I suggest you try this out for a minimum of 15 minutes, ideally 45 to an hour, not more than 2 hours. If you'd like to go along with us, give it a go for the next 5 to 10 minutes. And you might be surprised, you might think, wait a second, so like one solution I saw that somebody posted was, it's a fake solve. Well, for I equals 1, we have this 0. For I equals 2015, we have this is 2015. So we have all numbers from 0 till 2015. Now, why doesn't that work out? Well, for one, here you have 2015 values. From 0 to 2015, you have 2016 numbers. So it can't work out. But secondly, you're missing that not all numbers will necessarily be represented here. So what do we do here? Well, it seems, how do we even count? Like at the beginning, we're going to have zeros until we reach to a square that's bigger than 2015, but less than 4,000. And then, which I think 45. And then we're going to have a bunch of ones, a couple of ones, and we don't know how many ones. And then a 2, maybe one. Like, it's really hard to figure out like what's happening here. So the first thing for us to do is to play around. Now you might say, wait, am I going to write numbers from 45 till like 100 and something like, is that what I'm going to be doing? And I'm like, no. Instead of 2015, let's solve the same problem, but for say 5 or 15 or some number that's smaller, so we see if there's a pattern. And if we do that right here, I invite you to pause for the next 10 minutes and try to do that. And here's a list. And what we see is we got, okay, 0, 0, 1, 3, 5. So maybe we get odds after we get a 1. And then you see, okay, n over 15, n squared over 15, we get 1, 1, 2, 3. Okay, we don't really get odds. Okay, so then the next maybe hypothesis would be, okay, after we're done with the doubles, then we will never have a double again. And then you try, okay, n over 20, n squared over 21. And you get 0, 0. You get 0, 0, 1, 1, 2. Okay, now do we have doubles? But wait, we have 3, 3, and then 4, 5, 6, and we're skipping a 7. What is happening here? What is this thing? Why do we get some numbers twice, some not twice? And when we look at this number in general, this whole problem in general, what we're going to see is that we're going to be getting like, okay, I squared over 2015. If this is equal to k, that means that 2015k is less than I squared, is less than or equal to I squared, and this thing is going to be strictly less than 2015k plus 2015. So I squared is between these two multiples of 2015. Now we don't know how many multiples there could be here. Like we could have this be very close to 2015 k, and then I plus 1 squared could be inside again, and then so could I plus 2, right? So if we have, say, I plus t squared, we're going to have I squared, which is, at least this, plus 2it plus t squared. Now this thing, well, maybe we can, say how big it is, how small it is, whatever, but what do we do here? I invite you here to pause for the next 10 to 15 minutes and try to push the problem further. Does this inspire you in any way, shape, or form? What do you see? Pause now. And the next thing for me, then this was the idea that I got was, okay, wait a second. I'm going to have I squared, and then I plus 1 squared is going to be in the same interval under what condition? Like, when is it definitely not going to be in the same interval? Because if you think about it, if I know that I plus 2 squared isn't in the same interval, definitely, then I can, I can say, I don't need to know what it actually is, but I can figure out how many of numbers are of this form. It doesn't tell me what numbers are of this form. It says how many are of this form. And what I'm getting is, okay, I plus 1 squared is going to be I squared plus 2i plus 1. And this isn't going to be here if and only if this is greater than or equal to 2015k plus 2015. Now, because this is greater than or equal to this, I know that if 2i plus 1 is greater than or equal to 2015, then I know that the number that these I squared, I plus 1 squared, I plus 2 squared, and so on and so forth over 2015 and the floor of that, they will all be different. What is it? This is equivalent to I greater than or equal to 107. So if I is greater than or equal to 107, so starting from I, 107, to 2015, we're going to get distinct numbers here. And it doesn't matter what those numbers are, right? For us, it doesn't matter. For our intents and purposes, find the number of different numbers of this form. We care to say how many there are. Okay, so starting from 1007, we're going to have an easy, we can count up those numbers. Now the question is, what happens with numbers between 1 and 1006? That seems to be where the difficulty lies, right? Because now, I mean, say if we knew that 2i plus 1 was definitely less than 2015, I mean, if it was less than maybe half of this, then we could maybe say, okay, we're going to have two numbers here at the minimum. So if I was less than 600, well, actually about 500-ish, 503, we know we have two numbers around there, definitely. But how do we do this? I really, really urge you to pause now and try to think of the next step. And for me, the next step here was, okay, wait a second. I was actually thinking about this 503, this thing I just mentioned. What happens if I have I there? And then I thought, wait a second. This number before is going to be 1006. Just looking at this thing right here is actually where I got this idea. Well, see, when I had 15, this equivalent for I, 2i plus 1, is 15, if and only if I is equal to 7. So for 7, I got all the numbers between 0 and 7, between 0 and 3. For 21, 2i plus 1 is 21, I is equal to 10. From 1 through 10, I got all the numbers from 10 squared over 21, from 0 squared to, from 1 squared over 21 till 10 squared over 21. I got 1 through 4. So could it in fact be that between 1006 over 2015, the squared over 2015, from here to 1 squared over 2015, from a0 to whatever this is, that I'm going to cover all of these numbers? Could that be it? And now I invite you to pause for 5 minutes and ask yourself that and maybe answer the question. And the answer is, yeah. Why? Now that is actually the big deal. Why is this the case? Well, if you think about it, what does it mean we will cover every number? So if we covered, say, if we got a k, right? We got I squared over 2015 is equal to some k. We want to say we will not skip over k plus 1. But say we got I squared plus I plus 1 squared over 2015. This floor is k plus 2. We skipped over k plus 1. Right. What does this mean? What do these two equalities imply? Well, this one implies the following. But this one implies that I squared plus 2i plus 1 is at least 2015k plus 4,030. Now, we know this. Now, we want to say that this can't be the case, but how are we going to estimate this? And also, mind you, keep in mind that in this case, I is less than, it's less than or equal to this. I mean, less than or equal to this and 5, 1005. This is the border where we might have some issues here and there, but roughly less than 1005. Now, what does this imply? Well, if this is less than 1005, then this is less than or equal to 1005 plus 1 squared, so this is I squared, plus 2 times 1005, which is 2010, 2011. I squared plus 2011. Now, this thing right here, 2015K. Well, 2015K plus 2015 is strictly greater than I squared. So this is greater than I squared, plus take 2015 out of here, plus 2015. And we get 2015 plus I squared, 2011 plus I squared, a contradiction. And this is how you can prove that. This is a proof for why this is the case. And also we can now say what is enough. Okay, we had 2015, so we can even say I less than or equals to 1007. We're going to have this. We're never going to skip over a k, right? And this is now crucial. This means that we'll cover all the numbers from 0 to this number, right? All the natural numbers from here. Like we can never skip over, because our I is less than or equal to 1005, but 1007 also works. And now with that, what is this number over here that we're going to get? Like this is also a bit of a tricky sort of thing for me. Also, what I was doing is I was trying to calculate, okay, what is this number? What is 1007? To actually make sure that we get the number that we want to get. Now, for me, I was looking at this, okay, let's say 1006 is equal to k. Like this is going to be roughly, if I'm thinking like this is roughly k, this is roughly 2k. K squared is 2k. I'm going to need k over 2, so let me say 1006 is, so 2k squared. K is equal to 503. And here I'm getting like 4k plus 3. I'm getting this number, right? And I'm trying to say like this is in the vicinity of k, which means what? Well, let me clear this up. This is going to be around k, which means it's either less than k or greater than k. Now, is it less than k? Well, the answer is yeah, it's pretty much less than k, because now when I multiply this, I'll get 4k squared. Over here, I'll get 4k squared plus 3k. So this is definitely greater than k. Now, is it, like this is less than k. Now, is it greater than or equal to k minus 1? Roughly in that vicinity. And the answer is, well, what do I have? I have, when I multiply these through, I'll get 4k squared. And then, like this is just plainly multiplication. Minus 1 times 4, minus 4k, 3 plus k plus 3k, minus 3. And what do I get? And here I have 4k squared. These cancel out. This is true if and only if k is, actually k plus 1 is greater than or equal to 0, which is true. So here, what number I'll get from k is equal to 503, the number I'll get is k minus 1. So I'll get k minus 1, which is 502. So from 1 through 1006, I'm going to get all the numbers from 1 till 502. And then for the other numbers, for 1007 till 2015, I'll always get distinct numbers. And it's also good to double check the work, double check values. 1007, 1008 also give us two distinct numbers, just to make sure you haven't messed up the algebra anywhere. If I have, it's going to be very funny, but I don't think I have, because I'm not going to check my work on camera. And what happens is, okay, we have a 500, actually no, 0, so 503 numbers here. And then here we have, okay, when I subtract 1006, I get 2015 minus 1006, which is 1009. So 1009 plus 503 gives us how many numbers? It gives us 1512, 1512 different numbers of this form. And I thought this was a very, very, very cute problem. A very good one, in fact, because you think at the beginning, oh wait, this is going to be a walk in the park, and then you try it out, and you're like, wait a second, how do I actually work with this? How am I going to figure out the distribution of squares with respect to 2015? It seems very, very difficult. And then you realize, wait a second. I don't have to. Because I only care about how many of them there are. I don't care which ones there are. And I don't have to calculate the distribution to figure out how many of numbers are of this form. Right? That's the actual cool part about this problem here. You might think I need to get the distribution to get the number of numbers of this form. Then you realize, wait a second, I don't need that distribution to actually show that there are a specific number of numbers of this form. And this finishes up our problem. And as always, thanks for problem solving.